So the space beta x, this is a Stone-Check compactification of x, is usually very much larger than x. In particular, it is almost never true that beta x is the one-point compactification of x. For example, if x is equal to interval from 0 to 1, with 1 at 0 is open and 1 is closed, then the one-point compactification of x is just 0, 1. However, sine of 1 over x in CB, C sub b of x, this is a bounded continuous function on x, but it has no continuous extension to 0, closed interval from 0 to 1, because at the point 0, this vibrates infinite many times. So it has no continuous extension to this interval from 0 to 1. This is the one-point compactification, but it has continuous extension to beta x. No extension, no continuous extension to 0, 1, and it has a continuous extension to beta x. So beta x is not equal to interval from 0 to 1. Corollary 6.4. If x is completely regular and mu is in M of beta x, so this mu, this M of beta x is Borel measure on beta x with finite variation. And total absolute value measure is finite, is not infinity. So mu is a member of this set. Okay, and this is the dual of continuous function on x, on beta x. This is the dual identified with the dual of continuous functions on beta x. So if mu is here, then we define L mu from CBx to F by L mu F equals beta x integral over beta x F beta d mu. This is the continuous extension of F to beta x. So this is, we define this L mu by this for each F in CB of x. Then the map from mu to L mu is an isomorphism of M beta x onto CB of x star. Proof. It is clear that CB of x and C beta x are isometrically isomorphic, because each function in CBx has a unique continuous extension. So in the theorem, we only say it has a continuous extension. the extension is unique because X is dense in beta X. And the norm of these two spaces are just the soup of the function. So obviously this is just a continuous extension to the closure of X. So they have the same norm. So that's why they are isometrically isomorphic. By theorem 357 on page 75, these two spaces, this Borel measure, finite Borel measures, and is identified with C of beta X dual star. These two are isometrically isomorphic. So the map mu, L mu, is the composition of the two isometric isomorphisms. One is this, we mentioned it here. The other is this one. The other is this one. That is because these two, without star, these two are isometrically isomorphism. Yeah, without the star, these two spaces are isometrically isomorphic. Now with the star, they are still isometrically isomorphic. So that is the end of the proposition. Now we have theorem 6.6. If X is completely regular, then CV of X is separable if and only if X is a compact metric space. Suppose X is a compact metric space with metric D. For each n, let use of K of n, and K is from 1 to n of n, be an open cover of X by balls of radius 1 over n. So each point, you have a ball, okay? Then this is a cover, but because the space is compact, so you can choose a finite number of these balls to cover X. So by balls of radius 1 over n. So with this fixed n, we can have a partition of unity subordinate to this. This means what? This means the support of this function, fk of n, is included in this open set. And this function, the sum of these functions is identically equal to 1 on the space. The sum equals 1, and each of these functions has has support inside this open set. And also the function has value from 0 to 1. So such a finite sequence of functions with these properties is called partition of unity. Okay, and the existence of such partition of unity is in standard textbook of topology. Also, this is in our real analysis, we have this theorem. So we have this partition of unity subordinate to this UKN. Let Y be the rational or complex rational linear span of these functions. Rational, so if the space is real, if we are consider real functions, if our scalar field F is real, then we take rational linear span. That means we get linear combinations, the coefficients with the coefficients being rational numbers. If we work with complex numbers, if our F is complex numbers, then we take a complex rational. Complex rational is a rational number plus I times another rational number. These are called complex rational numbers. So we take finite linear combinations with rational or complex rational coefficients. These are called rational or complex rational linear span of these functions. So this Y is countable because this is this is a finite set, and the coefficients, rational numbers, are also countable. So Y is countable. Now it will be shown that Y is dense in C of X. So if we can prove that, then C of X is separable by definition. It's separable by definition. So now we are going to prove that Y is dense in C of X. So in order to prove it's dense, for given we fix F, C of X, and epsilon greater than 0, we want to find the function G in this Y so that F minus G norm is less than epsilon. So for given F, we want to find a member Y which is epsilon close to F. So there is a delta greater than 0 such that F of x1 minus F of x2 less than epsilon over 2. Whenever D of x1, x2 is less than delta. This is so because F is continuous and X is compact. Okay, because F is continuous, X is compact. A continuous function and the compact space is uniformly continuous. That's why for this epsilon, we can find the delta so that fx1 minus fx2 absolute value is less than epsilon over 2 whenever d of x1, x2 is less than delta. So this is because X is compact. Now we are going to choose n greater than 2 over delta and consider the cover. We fix this n, then we consider this cover of X. If x1, x2 is in this set U sub k n, then dx1, x2 is less than 2 over n, because this uk of n is a ball of radius 1 over n. So the diameter is 2 over n. So any 2 points in this ball has a distance less than 2 over n. This 2 over n is less than delta because this. Because this is less than delta, then by what we say here, if the 2 points are has a distance less than delta, then the function absolute value less than epsilon over 2. Okay. So now we can choose an arbitrary point in this set. Then we choose alpha k in this set such that alpha k is less than f of xk. Absolute value is less than epsilon over 2. So then fx minus alpha k absolute value is less than epsilon for x less in this ball. This is because of the triangle inequality. Because this absolute value, this distance of the two numbers is less than or equal to fx minus fxk. So you use absolute value. This is less than or equal to this plus fxk minus f of x, absolute value. So this is less than this difference, and another difference has this form, use the xk here, x here. So this is less than or equal to this plus absolute value f of xk minus f of x. This is less than epsilon over 2. And the other term is also less than epsilon over 2 because of this. Because what do we say here? And for any 2 points here, you get less than epsilon over 2. So by triangle inequality, this is less than epsilon for every x in UKN. So let G be defined by this sum over k. Alpha k, this is the number, f, n, k. This is the function. This is this group of functions is called the partition of unity. Okay. So G is in Y. Yeah, this is because these are functions with rational or complex rational coefficients. So this is in Y. So therefore, for every x in big X, we want to estimate this difference. Absolutely. This is equal to absolute value outside. The inside, we get this. Okay. So now fx times this, if you take a sum, you just get the fx. And alpha x times this, you take the sum, you get the g of x. So that's why this is equal to that. This is equal to that. So then when we mentioned that for the points where this is non-zero, if this term is non-zero for fixed k, if this is non-zero, then this x is inside of this. Other places is 0, so then we don't think, we can ignore. For the point x, this is non-zero, then this must be in this set. But if x is this set, this is less than epsilon. absolute value of this is less than epsilon. So this is less than epsilon. Yeah, from here to here, that's just the triangle inequality. But here, this is less than epsilon because what do we say here? Okay, for if this term is non-zero, then x must be ukn. Then this must be less than epsilon. So we have that. Then you can take this epsilon out. Then you sum this function. The sum of this is 1. So this is just equal to epsilon. For every x, this absolute value is less than epsilon. So the norm Fg is less than epsilon. And why? Because for every function f and for given f and given epsilon, you can find the g so that this norm is less than epsilon. So this means y is dense in C of x. If y is a dense, countable dense set in C of x, so this shows that C of x is separable. So we have proved one direction. So this shows that C of x is separable. So now assume that CB of x is separable. We want to prove that x is compact. So, but if this is separable, then this is metrizable. Theorem 5.1. This is metrizable. It follows that x, beta x are metrizable. This x and beta x are metrizable. Okay, x and beta, because these are subspaces of that. These are metrizable. It must be shown that x is equal to beta x, because this we know that this is compact. We want to prove that the beta x is compact. Beta x is a closure of x, okay? So if x is, we need to prove that x is compact. So we must prove that it is closed. So we must prove that it is equal to its closure. So now we are going to use proof by contradiction. Suppose this is not equal to, x is not equal to beta x. Then there is a tau in beta x minus x. Okay. So let xn be a sequence in x such that xn goes to converges to tau. Here we say you have a sequence, okay, which converges to tau. This is because beta x is the closure of x. So you can have a net converging to tau. But how do we know? In general, we cannot say there is a sequence converging to tau. But here, because beta x and x are both metrizable, this is we are working in a metric space. So then, of course, we can find a sequence converging to tau. And then if we get a sequence, then if we remove repeated terms, we can assume that these terms are all different. So we can have a sequence xn converging to tau, and xn is not equal to xm for n not equal to m. This says all terms are different. So that you take one set A. A is the set of even indexed terms, and B is the set of odd indexed terms. Then A and B are disjoint closed subsets of X. We must understand these are closed in X. They are not closed in beta X, okay? Because in beta X, they have a limit point tau. They have a limit point tau. They have a limit point tau. It's not in the set. If a set has a limit point outside of the set, then it is not closed. So these two sets are not closed in beta X, but they are closed in X because they contain all of their limit points in X. The limit points of these two sets, just the set itself, okay? You cannot have, because this is discrete in X. So these are disjoint closed subsets of X. Since X is normal, so normal, a topological space is normal if every pair of disjoint closed sets have disjoint open neighborhoods. And every metric space is normal. So here we use these are metrizable again, okay? We use this metrizable again. So every metric space is normal. So X is normal. So A and B are disjoint closed sets. Then by a theorem in topology, there is a continuous function f from X to 0, 1, such that f is 0 on A, f is 1 on B. F is 0 on A, and f is 1 on B. But then f beta tau, that is a continuous extension to beta X. So the value tau, because these points converging to tau. So this beta tau is equal to f of x to k for even terms. It is 0 because f 0 on A. And f beta of tau is equal to limit of these odd terms, then it is equal to 1. So the same number is 0 and it is equal to 1. So this is a contradiction. So this must be empty. So that means X is equal to beta X and X is compact.